Hi, and welcome back to my short lecture video series. Today's topic is going to be sound and ultrasound, and in particular using ultrasound diagnostics and how to use echolocation and that kind of thing. So what we have here is a simple chart that shows what are called isocontour curves of loudness. So FON is the measurement for loudness in human hearing. If you follow the cursor going along one of these red curves means these sounds all are perceived as having the same loudness by a person with normal hearing. So this one right here would be 120 FONs worth of loudness. This would be 110 FONs worth of loudness. Down here 20 FONs worth of loudness. 60 FONs worth of loudness. 0 FONs. You'll notice a few things about these curves. First of all, they have a low point and a high point. Essentially, the lower the curve is, the more sensitive we are at that frequency. So this x-axis is your frequency of the sound wave. The y-axis is the sound intensity level in decibels. We've discussed this and actually this in previous videos. Note that these are both logarithmic scales because sound intensity level beta is itself logarithmic, and this scale is shown as logarithm. So if you were plotting intensity versus frequency, this would be a log-log plot. Alright, so the lower the curve dips, the more sensitive our hearing is to these curves. We are most sensitive around 3,000 to maybe 4,000 hertz depending upon what loudness level we're dealing with. Second thing to notice, it is possible to go below 0 on the decibel scale. Remember that decibel is a log base 10 of some intensity divided by a reference intensity. In sound waves, the reference intensity is 10 to the minus 12 watts per meter squared. So negative 10 just means you have something that's lower than that. It would be more like 10 to the minus 13 watts per meter squared. Other thing to notice about it is they all start at about the same place. They all stop at about the same place. And this is not accidental to this scale. This scale actually starts at around 20 hertz. It stops at around 20 kilohertz or 20,000 hertz. The reason for that is that normal human hearing runs from about 20 hertz to 20,000 hertz. If you go below 20 hertz, you still have a wave. It's still even a sound wave. It can be heard by, you can design an instrument to pick it up. It can be heard by certain animals like elephants actually have lower threshold of hearing than we do. But anything below 20 hertz is called infrasonic. Anything above 20 kilohertz would be called ultrasonic. Now, as I mentioned, there are some animals that can hear in this range. There are also some animals, perhaps more famously, that can hear in this range. For example, I believe a dog, the upper threshold is something like 45 kilohertz, so 45,000 hertz compared to our 20,000. And a bat, I think, can go to something like 100 kilohertz, so 5 times higher than our upper limit. And so basically, if you have a dog whistle, you blow on it, it emits a sound at 30 kilohertz. This is well beyond our hearing, but it's well within the dog's hearing. Even 25 kilohertz would be beyond our hearing, but well within the dog's hearing. So you can make these whistles to call dogs that don't bother the people, that the people can't hear, but the dogs hear just fine. Likewise, a bat has a very high threshold of hearing. And part of the reason for that, part of why that's an advantage to a bat, is because the higher the frequency, the shorter the wavelength. And the shorter the wavelength, the better the resolution. One rough estimate is that the wavelength is roughly the same length scale within a factor of like 2 or so. Same length scale as the smallest thing that you can resolve with that wavelength. So remember that speed of a sound wave or of any mechanical wave, any wave in general, is the wavelength times the frequency. So wavelength is therefore speed over frequency. So the bigger the frequency, the shorter the wavelength that you can resolve. So for comparison's sake, let's consider a person versus a bat. All right, upper limit of our hearing. Let's go to say 10,000 hertz, 10 kilohertz. Okay, remember that in air at room temperature at sea level, your speed of sound is about 343 meters per second. So at 10 kilohertz, lambda is going to be 343 meters per second divided by 10,000 hertz, or 10,000 per second. So the per seconds will cancel. You will end up with 0.0343 meters. This is about 3.43 centimeters as your resolution. Okay, or in other words, about 1.7 centimeters for your wavelength for the upper end of human hearing. Now consider what it is that a bat might be trying to locate via echolocation. Usually they're looking for prey, for example a bug. What size is a typical bug? Well, there are bugs that are 3 centimeters long or 1.5 centimeters long, but there's also many more bugs that are considerably shorter. So what happens if we go up to 100 kilohertz? Lambda now is 343 meters per second divided by 100,000 inverse seconds. So now that's 0.00343 meters, or in other words, 3.43 millimeters. And this is now your resolution limit. So how big is a bug? Well, you might recall from my Physics 1 first lecture set that the length of a housefly could be approximated as about 5 millimeters. So that's 5 times 10 to the minus 3 meters. So 3 times 10 to the minus 3, or 3.4 times 10 to the minus 3, 5 times 10 to the minus 3, we're looking at the same rough length scale here. In fact, 80 kilohertz would very nearly nail this thing. Okay, so you can see, or you can locate it via echolocation at 80 kilohertz, 100 kilohertz. You can't do that at 10 kilohertz. So that's sort of the first application for this. Second application of ultrasound basically is for use in anything from prospecting, basically looking for oil or natural gas or whatever, to trying to determine what kind of mineral or what kind of soil or rock or what have you have under your ground, to locating where the underground conduits might be, like if you have power lines underground or if you have a water line underground, you're trying to figure out where it is. You could use ultrasound to do that. And then obviously in the medical field we do the same thing, except for that we do it to look at organs within your body, or beyond just looking at organs. The probably most famous common use would be looking at a baby. So if you or your significant other is pregnant and you want to go look at your baby in the womb, then you use an ultrasound. So how does that work? First of all, why do we use ultrasound? Again, it's because the better, the longer the wavelength, the worse the resolution, and therefore the shorter the wavelength, the better the resolution. So by using ultrasound, we get better resolution images. Now there's actually a limit here, because the flip side to this is that when you're doing stuff like trying to send sound waves through somebody's body, the penetration depth depends on the wavelength as well. And so basically what this means is you don't want to have too short of a wavelength, because then you won't get enough penetration depth. So in principle, we can generate sound with gigahertz range. I think we have in fact generated sounds that are in the gigahertz range. But usually we're wanting to use, again, stuff that's more like 100 kilohertz, 200 kilohertz, somewhere in that range, because that is what will have enough penetration depth to actually see an infant in the womb, or for that matter, if you're looking at an organ, different organs within the human body. You need to have that penetration depth. Now, how this thing works is that you have a little transducer. It sends a signal, and then each time the signal passes through an interface, that's basically a boundary between two different materials, it will reflect part of it. That's basically an echo. Okay? So what you do is you send the signal, and you get two pieces of information back from the echoes. The first piece of information is how much time passed from when you sent the signal till when you got the echo. All right, so that's this time axis here. Now that basically tells you, because of knowing what time of flights are, that basically tells you how deep or far below the surface each interface occurs. The second piece of information you get is how strong the reflected wave is. That one gets you a few pieces of information, really. Mostly you use it to figure out what kinds of material there are on the two sides of this surface. So time of flight tells you how deep, strength tells you what kinds of material. So how does that work? Well, time of flight, basically you use distance traveled is speed times time, actually divided by 2 because you go there and back. For an echo, it's getting there and then coming back. All right, so if you know how much time it took and you know what the speed is, then you know what the depth is, or the distance. So how do you know what speed it's moving at? Well, actually the strength of the signal helps you determine that. Because it turns out that this amplitude, let's call this A reflected. So you send in a signal that has some large amplitude like this, A naught. Well, it turns out that this ratio, A reflected over A naught, is defined as amplitude reflection coefficient little a. And it turns out that that amplitude reflection coefficient little a is given by the difference in a thing called impedance squared divided by the sum squared of those impedances. So what determines impedance? Well, impedance is just given by the wave speed times the density of the material. So this is what's called impedance. This is the density, and this is the propagation speed. All right, so basically you would then pull up a chart like this, and again, Z is rho times V. You'd pull up a little chart that tells you different densities of material, and then what the expected speed of the ultrasound is, again bearing in mind that for something like air, this right here is going to depend upon temperature. And then you may even know what the acoustic impedance is. So just as a quick double check, let's calculate the acoustic impedance for air given this speed and given this density. So Z for air should be 1.3 kilograms per meter cubed, that's the density of air, times 330 meters per second. I think actually this is using 0 degrees C. I think ultrasound is maybe a little slower than regular sound. So I guess this is not room temperature, it's 0 degrees C. 1.3 times 330 gives us 429. So we come over here, 429 kilograms per meter cubed dot second. This would be our answer, and sure enough, that's the answer given here. So if we know what the impedance is for a given material, then we should be able to figure out what, for two materials maybe I should say, then we should be able to figure out what the relative amplitude of reflection is from the interface between those two materials. So coming down here, let's say that you have a layer between fat and muscle. All right, so fat and muscle. What is the expected amplitude of reflection for this layer? Well, again, your relative reflection, your reflection coefficient, should be the difference between these two squared plus the sum of these two squared. Okay, so come up to the chart and look up what these are. That's these two numbers, 1.34 times 10 to the 6, 1.70 times 10 to the 6. All right, and it doesn't really matter since we're squaring it what order we go in, but I believe that this is the order that it's written in. All right, and so I've pulled out the times 10 to the 6s, since it's a common factor of all of them. I pulled out the units because it's a common factor of all of them. Units should also be squared, but again, cancel, 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 cancel. We're left with this stuff. So we can plug it into the calculator to see what we get. 1.34 minus 1.7 is this. Square it, divide it by 1.34 plus 1.70 squared. And what we get is this number, 0.014. So this is basically saying that roughly 0.014 of this total will be reflected, or in other words, 1.4% of the incident. So if I have an incident that's like this, traveling towards the interface, then I expect to get something like this reflected back from the interface. Okay, and bear in mind that this is an amplitude, and as we saw in the previous video, amplitude squared is what gives intensity. So I think that's about all I have time for in today's video. Maybe a last word of why do we use ultrasound for diagnostics versus x-rays. X-rays tend to be able to detect stuff like bones very well, but they tend not to detect soft organs very well. These ultrasound can detect the soft organs. That said, x-rays have much, much, much better resolution than ultrasound. Our resolution, our practical resolution limit is on the order of 1 millimeter. Remember what we talked about with the bat and how it could see as low as of order like 4 or so millimeters. So, you know, and again, there's a factor 2, so maybe that's 2 millimeters. We're basically looking at the same. We're looking at about 2 millimeters of practical resolution limit. Maybe 1 millimeter if we're lucky. And the reason why is because our depth of penetration into a person is about 500 times the wavelength. So maximum penetration depth is given by about 500 times the wavelength. If our resolution limit is 1 millimeter, then our penetration depth maximum is 500 millimeters or half a meter. And if you're dealing with, let's say, a woman who is in the 3rd trimester of pregnancy, then half a meter doesn't actually go all the way through her at that point. It does get far enough to see the baby, obviously, but it doesn't make it all the way through the woman in question. And so what if you're in for something other than to look at the baby? What if you're in there because you're trying to find something on an organ? Well, you may have to get deeper than that 0.5 meter depth. So that's all I have time for today. Thanks for watching.